So again, the flags are easy to put on. I'm doing this for the benefit of the recording now. Datum feature, whatever feature we're going to add a datum to, we just select that edge, place the flag, and we're good to go. And we can modify flags so that they're on the same surface in two different views, as long as they have the same ID, alpha character, we're good to go. So as long as this is C and this is C, they're fine. If this was D, it would not be correct, or E, it would not be correct, because we'd be calling out two different datums for the same surface. So hopefully we're good with that. I don't think I have anything else open in SolidWorks at the moment. So, all right, we went through this guy, saw a couple of mistakes. Let's get started on the lovely PowerPoint. We're talking about limits and fits today. In the US, they are specified according to the ANSI standard B4.1 from 1967 with a revision in 2004. The three types of limits or fits that we have are running and sliding clearance fits, which are designated RC, locational fits, which are designated LC, LT, and LN, meaning locational clearance, locational transitional, and locational force fits. That's what the LC, LT, and LN stand for. And then we have full force fits, which are regardless of what the tolerances are on the shaft and the hole, it's always going to be a press fit or an interference fit. When we look at the numbers on these fits, we have to remember that the lower the number, for ANSI fits, the lower the number, the looser the fit. So let's look at some. We're going to talk about shaft in the hole that have a basic size of 1/2 inch. And the fit is an RC8. And we're going to calculate the limits for the hole and the shaft. And we're going to use the limits and fits table that is in Appendix A. It's on page A-3 in the book. If you have it handy, open it up and take a look at that page. If you don't, this is it on the slide. So this is what it looks like, and we said previously that the class of fit was an RC8. So you just kind of look over here to the class and say, until you find RC8. And then for the nominal size range in inches, we go down this column until we find a range that includes our basic size, which is 0.50. So that winds up being this row right here. And we just move over to where the column and the row meet. And we look at these numbers here, and these are our tolerances for the hole in the shaft for that class of fit and that size range of whole shaft system. So we look at the numbers, and what do they mean? We got a plus 2.8 and a 0 for the hole, and a negative 3.5 and a negative 5.1 for the shaft. So what do they mean? Does anybody know what they represent?
Is the nominal exactly 1/2 inch?
Yeah, our nominal is going to be exactly 1/2 inch. It falls within that range. That's all we need to know. So So what we're looking, when we're looking at these numbers, without even knowing what the nominal is, you should be able to identify what these numbers mean. So let me explain it. For some reason, and I'm not sure what the thinking was, these numbers represent the upper and lower limits of the hole in the shaft in thousandths of an inch.
No.
So the problem is that only the whole numbers are a thousandth of an inch. So when you see a number like this, that means it's actually 0, it should say 0.0028 thousandths of an inch, which is 28 10,000ths of an inch. So that's how you would write it out. That number is, if you wrote it out as an actual decimal number, it would be 0.0028. This obviously is 0. This number is going to be minus 0.0035, and this number is going to be minus 0.0051. If you see a number in here that's less than 0, which I'm not sure this table has, I don't think it does. Yeah, here we go. That's actually less than a thousandth of an inch. So minus 0.6 is minus 0.0006, which translates into 6 10,000ths of an inch. So this is something you have to be, you have to stay aware of as you're working with the ANSI, the ANSI limits and fits, and the inch limits and fits, because for whatever reason you have to translate this stuff into decimal numbers, and it just seems confusing to me, but there it is. There's not a whole lot we can do about it. So this is what we're looking at. So we're looking at plus 28 10,000ths to 0 for the hole, and plus 35 10,000ths to plus 50, or excuse me, minus 35 to minus 51 10,000ths of an inch for the shaft. So let's take a look at it in a table form and see if that will make it any clearer. So here's the same system. We've got a system of hole and shaft that has a basic size of ½ an inch and the fit of RC8. If we calculate the limits for the hole in the shaft, here's what we come up with. The Appendix A limits say that the hole is plus 2.8 to 0, just like we saw in the table, and the shaft is minus 3.5 to minus 5.1. So you have to convert them to inches. So when you convert them, this is what you wind up with: 0.0028 to 0, and minus 0.0035 to minus 0.0051. So again, this is 10, 100, thousandths, 10,000ths. So this is 2 thousandths. This is 28 10,000ths. No tens, no hundreds, 3 thousandths, and 5 10,000ths. So we've got 35 10,000ths. Minus 0.0051. 0, 0, 5 thousandths plus 1 10,000th. So 51 10,000ths of an inch. So whose mic is making that noise? Is that you? Is that you, Jonathan?
That ain't that big a deal.
Pardon me?
The whole chart's in thousands. That's all.
Yeah, you have to convert this.
Yeah, right. I got you.
That part. What gets confusing to people is as soon as we go below 1, and we have numbers like I showed you, 0.6, everybody thinks that's 6 thousandths because they forget about, the other side of the decimal point. So you'll see. I'll be looking at your paper. I'll be scrutinizing yours the most to see if I when you submit some of the exercises to see.
Okay, that's fair. But I feel like you do that anyway.
Yeah.
Just
Well,
kidding. Just kidding. I'm just kidding.
I know that's okay. I look at everybody's the same, but it's easy until you do it. Then sometimes it's not so easy. And you'll see when I go through this lecture today, I'm gonna ball something up here. I guarantee it.
Okay.
So let's look at the minimum and the maximum limits of the hole in the shaft. Here's the minimum limits of the hole in the shaft. Boris is with us now too. Howdy, Boris. Glad you could make it. So we're talking about limits and fits and inch limits and fits. We're looking at an RC8 class of fit in a system of a half-inch hole and shaft. So we went through the table of how to convert these numbers in the appendix to thousandths of an inch, because the ANSI tables don't give you the numbers directly. They encrypt them a little bit for some reason, I guess to try to make sure everybody's on their toes. I'm not sure what the deal is. So here's the minimum limits for the hole and the shaft. So the minimum size of the hole is going to be the basis minus the smallest variance, right? Or the smallest, the least amount that the hole can be, which is right on half an inch. So the minimum limit of the hole size is going to be half an inch. The minimum limit of the shaft size is going to be a half an inch minus the largest of the two. That's not really the right way to say it. You know, it all boils down to minimum or maximum material and minimum material or least material conditions is what it really boils down to. So we're going to get into that a little bit later. Suffice it to say that the minimum size of the hole or the shaft is going to be half an inch minus this number right here, which is going to give us a 0.4949. So that's the smallest the shaft can be, is 0.4949. 4949. Here's what the largest shaft and hole can be. So the hole will be half an inch plus the 0.0028. And that's going to give us a hole size of 0.5028. The shaft is again going to be the size of the shaft minus the other figure, because it's a negative number. Both of these numbers are negative numbers, so they're always subtracted. In this case, these are subtracted. This is subtracted from the basic size, but the other number is added to it because it's a positive number. If this were a positive number, then you would add it to the shaft, to the hole size as well. So that's probably the best way to look at it. If the number's positive, although I get a zero has no condition like that, does it? It's neither positive nor negative. It's just zero. Correct? It's only a whole number that is or a full integer that's can be positive or negative, if I remember that correctly. I don't know, I'm not using the right terminology. It's been so long. But I don't believe you can assign a condition like that to zero, plus or minus. You can say it's a number plus or minus zero, but you can't say zero is a negative number or zero is a positive number. Anyway, Anyway, I'm just trying to make this a little clearer, but maybe it's clear enough, and I'm just overworking it. So let's keep going. So 50 minus 0.0035 means the largest the shaft can be is 4965. It's still under the half-inch basic size, but it's still it's a good number. Okay, so maybe this will make it a little bit better, understandably wise. So we're going to look at a basic size of a shaft of a hole of 0.75 with a fit of LT3. So we need to look up a fit of LT3, and I'm going to forget what page that's on.
A6.
A6. Okay, it's actually getting dark in my office here, and I can't see the pages very well. So I'm gonna, since you can't, since I don't have my camera on anyway, I'm gonna step away for just a second to turn the light on. So we're looking at the shaft, the fit of an LT3 for a size range of 0.71 to 1.19, right? And that should get us in the ballpark. And it looks like our limits for the hole in the shaft are, for the hole, they're plus 0.8 and 0. And for the shaft, they are plus 0.6 and plus 0.1. So if we look at the limits for the hole and the shaft is going to be plus 6/10,000ths to plus 1/10,000th, right? So if it's plus 1/10,000th, then it should be 0.7501 to 0.7506. Or in this case, I wrote them the opposite way because the shaft is, in my opinion, you want to write it the top number first and then the bottom number for the shaft, because you start out with maximum material and you move to the least material condition. So when you're turning or grinding that shaft, you want to hit 7506, and if you miss it, hopefully you get into, you know, somewhere in between 06 and 01, and you're still good. So that's the way I look at the shaft. And then the hole, I'm going to do the opposite way, and I'm going to say that the limits for the hole are, because they're 0 to plus 0.8, going to be 0.7500 to 0.7508. Again, maximum material condition, right? Smallest hole. Least material condition, largest hole. And we're always talking about the, you know, in the case of a hole, the material that surrounds it, not the hole itself, because it has no material. So in this case, the shaft is all material. So the maximum, the MMC is 7506, and the LMC is 7501. The basic size is 3/4 of an inch. The tolerance is going to be the difference between the two. And it's just a regular, it's just a number. It's always the larger number minus the smaller number. So in the case of the shaft, the tolerance is going to be, what do you think? Anybody? So if I take 0.7506 and subtract,
5/10,000.
how much?
5/10,000.
Yeah, 5/10,000ths. So this should be 0.0005. If I do the same thing with the hole, it should be 0.0008. What's the maximum material condition of the hole? I mean, of the shaft. You notice that the way this, if you look at the, just as an aside, if you look at the table on page A6, it's all hole shaft, hole shaft, hole shaft, right? And what do they do when they make this table here? They do it the exact opposite. Now, I don't know whether they did that to make us think about it or they just weren't paying attention. In my mind, it's probably just confusing enough to people that you should probably not add to the confusion by listing the shaft and the hole exactly the opposite way that the tables do. I think every table does it that way. Hole shaft, left to right. But anyway, that's what they did. So what's the maximum material condition of the shaft? 7501 or 7506?
7506.
7506, right? Largest shaft. Maximum material condition of the hole.
7508.
The larger the hole, the less material.
Just 750.
Yeah, 750. Right? That's the least or the maximum material condition of the hole is the smallest size of the hole, leaving the most material around it. And easily enough, the least material condition should be the opposite. It's the other number, right? 7501 for the shaft and 7508 for the hole. What's the maximum clearance? Maximum clearance is going to be the smallest shaft and the largest hole. So when you look at these two conditions right here, when you put them next to each other, you've got the differences between them right here give you the max and the min clearance. The least material condition between the shaft and the hole should give you the maximum clearance, right? Does that sound right? Or does that make sense? Because the least material condition of the shaft is the smallest shaft, and the least material condition of the hole is the largest hole. So you have the smallest shaft going in the largest hole. That's going to be the most clearance you're going to have. So if you subtract 7508 from the 7501, you should come up with a clearance of 7/10,000ths of an inch. The smallest clearance, excuse me, is going to be the other two numbers. The largest shaft minus the smallest hole. Or, in this case, it's still going to be the hole minus the shaft. This was the hole minus the shaft. The hole minus the shaft. It's always the hole minus the shaft. So if we subtract 7506 from 7500, what do we get?
Negative 0.006.
Negative 0.0006.
Aye.
So that's another thing they have to watch out for is correct decimal places. Make sure you're working with the right number of decimal places, because we're talking in, the difference is in 10,000ths of an inch here. So we have to make sure we go the right amount. Yes, it's 0.0006. So when we look at these two clearances now, here we've got we've got a positive number for our maximum clearance. So that means that should tell us that we have space. So we've got a clearance fit when they wind up like this. When they wind up in the least material condition, we should have a clearance fit. When they wind up in the maximum material condition, we have a negative number. What does a negative number mean? If a positive number means clearance, a negative number means interference. So we've got a situation where on one end we have clearance, on the other end we have interference. So it's not a clearance fit, and it's because that would mean it was clearance no matter what. And it's not an interference fit because we would have interference in both ways, in both directions, or both extremes. And even in a line fit, we might have either clearance on one extreme and a line fit on the other, or we could have interference on one extreme and a line fit on the other. Either way, they're a line fit. And a line fit is determined or described by having one of the clearances, the extremes, either the max or the min, be a line-to-line contact. Usually it would be the minimum clearance, I would think. So this one is going to turn out to be what they call a transition fit. And that's the definition of a transition fit, where one extreme is clearance, the other is interference. How does that look? Are we all okay with that?
Yeah.
Okay. So let's move on to metric tolerances. So we're going to fill in the table here based on the dimensions that we see here. And it just so happens these are limit dimensions, so this should be pretty easy to figure out. It's the same as the ANSI system with some differences. Some of them seem like they might be a little more confusing, but they're not really. They're actually, it's much simpler to use and more direct. And you'll see what I mean in just a couple of minutes. So we're looking at the shaft and the hole. The shaft has limits of 2.2 to 2.1 on the diameter, and the hole has limits of 1.8 to 2.0 on its diameter. So if we look at the limits of the shaft, there it is, 2.1 to 2.2, and the hole is 1.8 to 2.0. What's the basic size of this system? 2. Yeah, metrics tend to go to even numbers. They don't have the range like the ANSI tables did, 0.41 to 0.45 to 0.71, diameter size or whatever. Or basic size is being relegated to even fractions, of an inch, like a quarter, half, 3/8, 7/16, maybe 1/2 inch, 5/8, and so on. They just go basically to even millimeter numbers. So the basic size of this system is a 2 millimeter system. The tolerance is going to be the larger number minus the smaller number in the limit. So the tolerance for the shaft is going to be 2.2 minus 2.1, or 0.1. The hole tolerance is going to be what? 2.0 minus 1.8.
1.2.
Yeah, which is 0.2. It's nice when you have limit dimensions on here to begin with. But even if you had bilateral, or plus minus tolerances, you should be able to figure out the not only the limits but the tolerances as well without too much trouble. So the metric system doesn't use the maximum material and least material condition. They use something called deviations, and they use throughout 3 different types really. They use the upper deviation and the lower deviation, and then they also use something called the fundamental deviation. And we'll get to all that. And again, it's totally different than what ANSI does, but when you see it and work through it a little bit, you might find that it's actually much easier to deal with than the ANSI tables. So here we go. The upper deviation is the difference between the basic size and the maximum permitted size of the part. The lower deviation is the difference between the basic size and the minimum permitted size of the part. And let's see what's on this one. The fundamental deviation is the deviation that's closest to the basic size. The fundamental deviation is the smaller of the upper and lower deviation. So in other words, if I say that it almost seems like the upper deviation and the lower, it would always be, or the lower deviation would always be the fundamental deviation, but that's not necessarily true. Because if they're negative numbers, then the larger negative number would be the, might be the, am I saying that right? The smaller deviation, the smaller number might be the upper deviation. So I don't know if I'm being correct in saying that or not. Anyway, it'll all be clear as mud in a few minutes. And I don't know why this is in here now, because of this, this just confuses things, but even more. But it says a letter in the fit specification represents the fundamental deviation, which is true, but we'll talk about that. So here's a similar situation to what we did with our inch shaft and trying to figure out the max and least material condition. So we're looking at this right now, the shaft and the hole. What's the upper deviation of the shaft should be, let's do the first one here, 0.2. Because the basic size of the shaft is 2, and the largest the shaft can be is 2.2. So our upper deviation is from the basic size is 0.2. Does that sound reasonable? We're all okay with that?
Yeah.
Okay.
That's
All
a
right.
basic size minus the largest size?
It would be the largest, it would be the upper limit minus the basic size. It's always going to be a positive number. It's always going to be a positive number anyway. So if we take the basic size, which is 2, subtract it from the largest number here, we get 0.2. Okay? For the hole, if we take the basic size, which is 2, and subtract the largest number in the limit of the hole, which is 2, we should get an upper deviation of 0. Are we okay with that?
Yeah.
Okay, so now the lower deviation is going to be the lower number in the limit of the shaft minus the basic size. So the lower deviation should be 0.1. And so now we're going to take the lower deviation, excuse me, not the lower deviation, the lower number in the limit and subtract the basic size, which is 2, and we're going to get we should get negative 0.2, but the deviations don't have they're not positive or negative numbers. They're just basic numbers. So the answer is still going to be 0.2. Okay. If I take this and subtract 2 from it, I should get a minus 0.2, but because there is no polarity to the numbers, for lack of a better, I can't think of the right word. You know, there's no positive or negative assignment to the numbers. What's the
So
fundamental? Go ahead.
Sorry, for metric then, it's always going to be the bigger number minus the smaller number for this?
Well, it's not the bigger number minus the smaller number, because it's this number minus the basic size, which is 2 millimeters. Remember, we said the basic size of this system is 2 millimeters.
Yeah.
Because the whole surround, you know, either equals to or surrounds the or is closest to 2 for an even number, and so is the shaft, right? 2.1 to 2.2. The basic size of the shaft is 2. The basic size of the hole is 2. So it's always the upper or lower number in the limits minus the basic size of the shaft.
Gotcha.
If I could write this on the board, it would probably help, you know. Unfortunately, we don't have that luxury anymore. The same thing holds true for the hole. It's the upper limit minus the basic size, which gives us 0, and the lower limit minus the basic size, which gives us 0.2. The fundamental deviation is the deviation that's closest to the nominal or basic size. So what's the fundamental deviation of the shaft? 0.1. What's the fundamental deviation of the hole?
0.
0, right? Yeah, because it's right on the money. So that would be the fundamental deviation of the hole. So when we look at this fit, here's
Line
where
fit.
Pardon me?
Line fit.
There could, no, there's not, it's not a line fit. A line fit occurs when when one of these numbers matches one of these numbers. In other words,
Oh, I thought it was 1, 1, 1. It was exactly 0.
no, that's not a line fit. That means this is automatically a fundamental. That this would be the fundamental deviation. This number
gotcha.
minus this
I
number,
gotcha.
yeah. We'll talk about line fit in a minute. But if you look at the fundamental deviation tells you what type of a fit you're going to have here. So if the fundamental deviation of the shaft is 0.1 and the fundamental deviation of the hole is 0, what that's telling me is that the shaft is always going to be larger than the hole. And if you look at these numbers, that's true, isn't it? If you look at what we call in ANSI the least material condition of the hole, the largest hole and the smallest shaft, the shaft is still larger than the largest hole, isn't it? By 1/10 of a millimeter. By 1/10 of a millimeter, it's larger than the largest hole. Than the largest size the hole can be. And that's what I see here for fundamental deviation. I see the 0.1 here and the 0 here, from here. So the fundamental deviation tells me what I'm looking at. Am I looking at a clearance, a transitional, or a interference fit? So what do you think? What am I looking at?
Would that be interference?
Yeah, it's going to be an interference fit, no matter what. It's either going to be an interference fit by 1/10 of a millimeter, or it could be an interference fit by 4/10 of a millimeter. And that's pretty big. Because 1/10 of a millimeter is what, about 4/1000 of an inch? So 4/10 of a millimeter is about 16/1000 of an inch. That's a pretty good press. I wouldn't want to have to be the guy trying to press it. So here's the types of fits that are available in the metric universe. Quite a few more than, although when you add up all of the, we looked at clearance, locational, and force fits in the ANSI standard. And it sounds like there's only three types of fits, but there's really more than that, because within each group, there's subgroupings, in the ANSI world. You've got, RC class RC 1, 2, 3, and 4, 5, 6, 7, and 8. And then you go from RC to LC to LT, and then those are locational transitional fits, and then LN are locational interference, and then force and shrink fits. And that's all of the fits that are in ANSI. The metric fits are there's probably less of them, but within each one of them, there's enough variance that you're going to cover all the bases that the ANSI fits cover. So, and this is how they're designated. They're either designated as whole basis fits or shaft basis fits. And when they designate them that way, if it's a whole basis fit, the H in this fit is capitalized, and this alpha character is lowercase. So if it's shaft basis, then the alpha characters that are designated for whole or shaft fits are capitalized and listed first, and then the whole information is secondary and lowercase. Again, it seems like it's going to be really complicated, but it's actually not that bad. So we go from an H11, C11, which is a loose running fit, to free running, close, sliding, locational clearance, transition interference, medium drive, and force fits. So, and if you notice, as these numbers go down up to a certain point, the fits get tighter. Whereas, what did it say about ANSI? As the numbers go up, as the numbers go down, the fits get looser in the ANSI tables. Isn't that right? The fits get looser as the numbers go down. So when you look at if you look at any one of the ANSI tables, and even just look at the very first table on A2, the very top line, a 0 to an eighth of an inch, basically. And now RC1, the whole is plus 0.2 to 0. And as we go to RC4, it's plus 0.6. So as the numbers go, well, maybe I'm wrong about that. Looks like as the numbers go up, the fits get bigger. So maybe they are the same. I thought that we had a slide that said that it was the opposite. I don't want to drive all the way back through just to find it, because it was right in the beginning. We'll look at the end. And again, I don't look at these things every day, so I don't pay that much attention to how they run. I just pay attention to what kind of fit am I looking for when I'm putting together a system with a rotating shaft that has to be supported, and I'm either going to use bushings, or I'm going to run that shaft right in the aluminum supports that are part of my machine, because my shaft is hardened and ground, and the aluminum is nicely machined. It's a good bearing surface, and all I got to do is add a hole and a Zerk fitting so somebody can pump some grease into it every now and then, and it should be fine. And people do that all the time. Any of you that drive a vehicle with an overhead camshaft, there's a pretty good chance that that camshaft is not running in any removable bearing shells, it's running right in the aluminum head, and that surface that it runs in is, nicely machined with a good finish on it. And it's got an oil hole in it that gets oil pumped to it, and there's no bearing insert or anything like that, or bushing that it runs in that is going to wear out. It just runs right in the head. Okay, so here's what we're looking at. When we look at a call out for a size and a fit, we look at the number that's called out as the basic size. Well, that's usually the diameter of the shaft, whether it's 30 or 31 or 45 or 50 in this case. That's the basic size. The H represents the fundamental deviation. So the fundamental deviation, again, is the closest deviation to the basic size. So if we have a deviation of the hole, or a limit, an upper or lower limit of the hole that is the closest to the basic size, that hole, the hole becomes the type of fit that we're looking at. It's a hole fit versus a shaft fit. If the shaft happens to have a fundamental deviation that's closest to the basic size, well, then it becomes a shaft-based system. In this particular instance, it's a hole-based system, and that's why the H is capitalized, and it's also listed first. And then we have this number here, which is an IT number, which is an international tolerance grade number. We're going to talk about that in a minute. This is also an IT number right here. So this represents the hole tolerance zone, and this represents the shaft tolerance zone. So when you look at the tables will tell you fully what that tolerance zone is for the hole in the shaft, based on this size of a shaft. You'll see it's actually pretty easy. So when specifying the hole, the fit, like it says here, it says the hole is the uppercase letter. That's if it's a hole-based system. If it's a shaft-based system, then the shaft is the shaft letter is the uppercase. The international tolerance grade number, the numbers are sets of tolerances that vary within the basic size and provide the same relative level of accuracy within a given grade. What the heck does that mean? Here's what it means. Regardless of what that number is, whether it's an H, whether it's an 11 or a 6 or whatever it is, there's going to be an upper and lower limit for that particular size shaft and that particular set of tolerances, and their accuracy is going to be the same as it is for the number 7 as it is for the number 11. In other words, the variance between them is going to be such that you're not going to get a situation where you're going to have too much clearance on one end of the spectrum and not enough clearance on the other end of the spectrum. For example, it just is a number that it just basically tells you that the fit is going to be as accurate for a number 7 as it is for a number 11. It might be looser or tighter, but the variance between the two numbers is going to be fundamentally the same. Might not be the same exact difference in thousands, or hundredths of a millimeter or tenths of a millimeter, but it's going to be on the whole, the difference between the upper and the lower are going to be such, like I said, that you're not going to be too tight or too loose for one reason or another. So it does indicate a smaller tolerance, tighter tolerances as the numbers go down. So the difference between the upper and the lower is going to be less for a number 7 than it is for a number 11. But the accuracy of those differences is not going to change. And there's no definition on this slide for the tolerance zone. that's really, truly, totally understandable. But here's what it says, right? The IT number establishes the magnitude of the tolerance zone or the amount that dimension can vary. Well, yeah, it does. I mean, so do the limits, The fundamental deviation establishes the position of the tolerance zone with respect to the basic size. So if I was able to draw on the board, I could draw you the size of the tolerance zone, and then I could insert the basic size within that tolerance zone, and you can see what the difference is between the two. But I can't do that. The best thing that we can do is go through this example of this fit. It's an H11 C11. We're going to do it in a table, I think, just like we did for the others. It says Appendix A of HC11. I think it's A9. Pretty sure that's on A9. So if you look on page A9, and again, I think I've got it in here on this slide. This is what it looks like. We cut away part of the page here, but page A9, if you look on the left-hand column, it says loose running, and you look at all the different classes of fits are labeled for you right here. This is a table of hole-based systems. So all of these fits are capital H, lowercase, whatever for the shaft. C11, D9, F7. The holes are H, capital H11, H9, H8, H7. These are all hole-based systems. That means that if you look at every one of these sets of limits, you're going to find a limit for the holes that's exactly the same size as the basic size. You see that? We've got a limit here of 1. 1 is the max size for this group. A 1 millimeter diameter shaft, that's pretty small. Right? 40 thousandths of an inch, pretty small shaft. Here's a 1.2 max. So that's anything. So that's from 1 to 1.2. Anything greater than 1 and greater than or less than or equal to 1.2 falls within this category. You're going to find a limit for the hole that's exactly the same size. Exactly the same size. Blah, blah, blah. All the way down the line. That's what makes it a hole-based system, is the fact that there's a limit for the hole that exactly matches the basic size. Well, here's our information right here. And guess what? Do we have to translate a bunch of hieroglyphically, placed numbers? 0, 0.6, 0.8, 2.3? No. To find out what our size is, we don't have to go 30 plus whatever the heck this translates into. The numbers are given for us right there. Here's the size of the hole. It can be 30 millimeters up to 30.13 millimeters. The shaft can be 29.76 millimeters, or if you want to read it the other way, can be the largest size of 29.89 down to 29.76 millimeters in diameter. The numbers are right there, nice and easy. And the columns tell you what type of fit you're looking at here. So when you're designing a system, like my shaft that I'm going to have either sliding in and out, back and forth, or rotating in between my two upright columns, I'm going to decide, do I want a sliding, close running? What type of fit do I want? Locational clearance? Depends. I got to look at what I got here and see how much clearance I'm going to have, and maybe do some calculations on what kind of heat I'm going to generate and this and that, and what kind of clearance a grease film or an oil film needs in order to survive in between those two and not get squeezed out, or have a clearance that's so big that the oil film or the grease film can't do its job. So I have to consider that, when I consider what my fits are going to be. but it seems to me to be a whole lot easier to do it with the metric chart than it is with the ANSI chart. So anyway, there's our information for our shaft, right? It's a 30 millimeter shaft. And by the way, this is supposed to be a diameter symbol. Remember, I don't know if you remember, I talked about it in class. I said you're going to find that you'll see an N, and people will write an N in their answer, and it should be a diameter symbol. Well, this is because the font system that they used when they made this slide didn't support the diameter symbol. So when they went to the character map or whatever they used to insert that diameter symbol, the font didn't recognize it, so it puts in the lowercase n instead of the diameter symbol. But that's what that's supposed to say. That's supposed to be a diameter symbol. Okay. So that tells us we're looking at a 30 millimeter shaft, and this is our information. So here's our limits, right? We take them right from the table. We didn't have to do any calculating and converting to figure out, how many hundredths or tenths of a millimeter it was. It's just right there. So what's the tolerance for each one of these? Again, the tolerance is going to be the larger number minus the smaller number. Larger number minus the smaller number. Yeah, what's going on there? So in this case, if I take the 89 minus 76, because it's both 29s, I should get 13, right? 0.13. Looks good. And the tolerance for this one, again, should be 0.13. What type of system is this again? Is it hole based or shaft based, and why?
Whole base because it's got a capital H.
Well, that's true. But what makes it that capital H? What makes that H capital? Let me phrase the question. Okay. Remember we talked about fundamental deviation, and the fundamental deviation is the smaller of the two deviations for each one, the hole in the shaft. The smaller of the two deviations in this case is 29.76 for the shaft. This one's closer to the hole, to the basic size, 29.89. So that probably would be the fundamental deviation, or it would be the fundamental deviation for the shaft. What's the fundamental deviation for the hole? Which deviation is closest, or which number is closest to the basic size of the hole?
Oh, it's that simple.
It's that simple, right? This lands right on the basic size, doesn't it? Doesn't it? Our basic size is 30 millimeters. This particular number in the limits of the hole lands right on that basic number. So that makes this the fundamental deviation. That in turn makes this a hole-based system.
So if the 30 was on the shaft, then it would be
A shaft-based system.
Oh, okay.
That's correct. And then it would be capital C11, lowercase h11. We'll get there. We won't get there today, but we'll get there. We're going to do both. So yeah, that's all it is. To determine if it's a hole-based system or a shaft-based system, you just look for which one of the limits is closest to the basic size, and that'll tell you which one it is. That's why I said when you go back to that this table, these are all hole-based systems, because every one of the limits of every one of these shaft sizes, somewhere along the line, the hole lands directly on the basic size, right? 1.2, 1.2 for the hole, 1.2, 1.2, 1.2. They all land, the whole limits, the lower limits all land right on the maximum size, basic size. Just like ours does. So now look at this one here. Just for example, we've got two of them here that are the same, right? They both have, and there's probably another one in there. This one's the same. As a matter of fact, these are all the same. They've all got the whole, where a point where the shaft and the hole can be exactly the same size. But the hole, it's still a whole system. The hole still takes precedence. So I don't know what else to say about that. And these would be, if this is how it worked out, this would be line-to-line contact, wouldn't it? Right? Because if the shaft were 30 exactly and the hole were 30 exactly, they'd be line-to-line.
Just at a quick glance, is the tolerance always going to be the same?
Is it always the same? All I see is one number that's the same. All these numbers are different, aren't they?
Well, I'm looking here at like 6 is 30,
Where you look,
and the free running is 30, and then the shaft is a difference of 30.
where's the, let's
the
see, which one are you looking at? Which basic size?
Free running,
Yeah, and which basic size?
6
Any one of them?
max.
Pardon me?
6 is at.
6. Where's 6? I don't see 6. Oh, because I'm not looking at the
Oh,
book.
I'm looking in the book.
Oh, okay.
Is that's not typical though, that they're going to be the same?
I don't see, well, let me so it's 6.03, right? For the whole.
Yeah.
And then, so where do you see the same thing? Okay, so it's 30 thousandths difference right there. And what are you saying, 30 thousandths difference for the shaft?
Yeah. I'm just wondering if is that always the case? And I'm looking at some that it's not the case. So I was just curious if.
Yeah, so I'd have to say no.
Right.
So it looks like and you got to remember the fits that you're looking at, right? You're looking at a free running fit. So they're going to have some pretty good clearances. But if you notice that as the things get smaller, the clearances are a little bit smaller because or the limits for the hole, they change. The limits for the shaft change. But yeah, there's a run where everything's 30, a difference of 30 between the upper and the lower. And then you go to the next size, 8, and the difference is 36, right? 36, yeah.
I see. I just took a quick glance. I'm like, oh, they're all the same. That's even easier.
Right, but you have to remember that as the shafts and the hole get bigger and bigger, the clearances have to get bigger. You can't maintain a 2,000 clearance around a 30 millimeter shaft is how big? How big is 30 millimeters? It's about an inch and it's 6 millimeters. So it's about an inch and a quarter in diameter or so. Okay, so let's say now the shaft is 100 millimeters. Or 102. That's about 4 inches. Do you think you're going to be able to maintain the same clearances between a 4-inch diameter shaft and a 1-inch diameter shaft?
Yeah, I got you.
You can't. You have to, for the same type of fit, you have to increase the clearances because you've got so much more surface area. Every time that thing makes a revolution, when you think about a 4-inch diameter shaft, the surface area, the circumference is over 12 inches, right? Is that correct?
Yeah.
You take the diameter times pi, which is 3.14157. and you multiply them, and that's what you get for a circumference. So it's about 12 inches, give or take. It's a little bit more. So now you got 12 inches spinning at 1,000 RPM, 1,000 revolutions per minute. So that's 12,000 inches every minute that bearing, that clearance has to be able to remove heat from and everything else. You take a 1-inch shaft, that's only 3 inches, and you spin that at 1,000 RPM, that's only 3,000 inches. So that's a whole lot less, surface that is going to be revolving around those clearances. So it's going to generate a whole lot less heat. So you can get by with tighter clearances. The bigger the shaft, the more you have to increase the clearances in order for them to run and not weld themselves together. And that's why that's one of the reasons why big engines like these big diesels will only run, like train diesels or the diesels they have in the nuclear power plants for backup generators. They run at about 500 or 600 RPM, but you can live inside of one of the cylinders. The pistons are so big, you could set up an apartment in a cylinder, and when you get that much mass moving back and forth, you can only move it so fast. So anyway, that's the reason why we have tables like this with all these different fits, because depending on the clearance and the sizes and all that, everything varies. And that's what that IT grade number is referring to when it's saying that it's keeping the tolerances accurate regardless of the fit, because it's maintaining, it's doing exactly what we just talked about. It's changing the clearances based on different parameters, the size, the type of fit, and all that. That's what that IT number does. This is the one we did already, right? So do you have, it's a little bit confusing, but if you work through some of the problems, you will, as you work through them, you'll gain a better understanding. And if you got some issues, give me a call. Worksheet. This is being assigned today to GD&T worksheet number 1. It's a PDF. You're going to have to download it or print it somehow because it's not interactive in any way, shape, or form. And you're going to have to print it out and fill it out and then take a picture of it to submit it. There is a link here to a website. This is how you're going to fill this out. You're going to click that link, and it's going to bring you to this website. You can all see this? Is that correct? Yeah. Okay.
Yeah.
Thanks for letting me know. So to answer the questions, why do we use GD&T, for example? Go to look at the homepage here, and this information should give you enough to be able to answer that question. If not, then go to the introduction, which is the same thing. So there are also links in every one of these pages on different lines. So if I were to say, like the symbols here, it says GDT uses a system of symbols. If I were to select that, it's probably going to just overwrite this page. So I'm going to right-click it and say I want to open a new tab. I just like to do that because and so here now it's just listed all the different symbols, and you're going to need this information, and it'll show up, I know, on different pages as well when you fill out the symbology part of the sheet. But you see the symbol here? You see what's going on here? My font is not correct to show these symbols. So this is what it's doing. It's showing the alpha characters instead of the right symbols. So you got to make sure that you have the right font loaded in order to.
And what is that font called? Any idea?
There is I believe there's a link somewhere here to tell you what font that is. See, once again, the diameter symbol is an N. Spherical diameter is SN. So let's go back and look at this.
And the counter bore is an X.
Yeah, I know, it's not right. It says, this website requires that your browser supports the GD&T font. So, if I don't think I can change that in my settings here. I think I might have to go to my computer settings and say, hey, I need to include the GD&T font. You know what? I will investigate that and send you guys an email. Which I do. Without email, we'd be lost. But I don't think I can change my font in my settings here. This is a Microsoft Edge, so who knows?